number of folks that could log on. So off we go. Anyway, so today I want to cover a little bit about today's game rules, give a little bit about speaker introduction. I'm going to cover a little bit about the environmentally friendly drilling program, the program this project falls under, and then I'm going to turn it over to the experts about the technology. So thanks everybody for joining us, and we'll continue on here. So our EFD program, we started up this program about 11 years ago now. Back in 2009, you see that we won the Chairman Stewardship Award from the Interstate Oil and Gas Compact Commission. And just last week, we picked up the Oil and Gas Award for Excellence in Environmental Stewardship. So we're very pleased with some of our accomplishments. Concerning today's game rules, please mute your phones. This will enable us to ensure that the background noise is kept to a minimum. And our speakers today will also have their phones muted unless they're talking. So with that, we're going to try to ensure that questions are asked via the chat box. Then we will be able to ask these as they go on. We will answer those questions as they are being received. We expect today's webinar to last about an hour. It will be recorded and it will be available then on the EFD Systems website into the future. So our speakers today, besides me, is John Fox at ElectraTherm. And please mute your phones. And Loy Sneary at the Gulf Coast Green Energy. A little bit about our team that we have. I'm at the Houston Advanced Research Center, or HARC, that George Mitchell established about 35 years ago. Also on the management team is Tom Williams, who has his own company, this Low Environmental Impact Drilling Organization, and Dave Burnett up at Texas A&M University. We also have Gerhard Thaunhauser over in Europe at University of Leoben. Our team also consists of a lot of sponsors and advisors. We greatly appreciate their financial support as well as their in-kind contributions and advice that they give us. We see our major sponsors, well, all our sponsors listed here. In addition, we do receive funding from some environmental organizations, and they are our advisors as well. We collaborate with a lot of other folks. And again, please mute your phones. And we see our field trial team that we have going on, and it is all the universities and national labs across the United States that we work with. Again, I'll go back to our number one game room about please muting your phone and using the chat box for asking any questions that you may have. Our field trial team that we had up in the Bakken to do this, we are very grateful and want to acknowledge HES for having it at their operational sites. In addition to HARC, we have our ElectraTherm and Gulf Coast Green Energy team involved in this project. This is just one of several different field trials that we've done across the United States, as indicated here. You can see the whole slew of them. They range everywhere from the Marcellus out to the Utah and up to the Bakken, into Canada, and of course throughout Texas as well, and over into Mississippi. These field trials consist of everything related to site selection all the way through gas compression, including flaring and flaring reduction technology, such as what this particular one is. Our mission of our EFD program is to provide unbiased science to ensure that environmental and societal issues are all being addressed throughout all oil and gas activities. And if you want any further information, later on our last slide, we'll have different websites that you can check out and see. So I'm going to just briefly now mention our flaring project that we have going on up in the Bakken. This is with the Organic Rankine Cycle, the ORC equipment. And we also have another one that we have under discussion that we'll be doing concerning this last mile or CNG technologies, and another one that's still under discussion concerning flaring as well. The objective of all of these is to identify and test simple, robust technologies to reduce flaring. Our EFD program is a nonprofit. We're not in business to be in business. We expect others to do that. ElectraTherm and Gulf Coast Green Energy, for example, they do have a business to run. So our big thing is to address those environmental aspects, in particular here about flaring and air emissions aspects, and what technologies, what simple, what robust technologies can be used and is out there that need that little bit extra help through a pilot study to get the program started. So I'm going to turn it over now to John Fox. Like I said, I'll be monitoring the chat box here if you have particular questions, and I'm going to put my phone on mute just like the rest of you except for John, and we'll go from there.
Okay, thanks, Rich. This is John Fox. I'm the CEO of ElectraTherm. I'm based in Reno, Nevada. We focus on waste heat to power using Organic Rankine Cycle technology, which I'll briefly describe in the next slide. And we have 3 product lines, a small, medium, and large. For us is 35 kilowatts, a 65 kilowatt unit, and a 110 kilowatt unit. If you're not familiar with Organic Rankine Cycle technology, basically hot water is the fuel. So we take hot water into our machine and create electricity at the site. And I'll go into various opportunities in waste heat to power. There's lots of different markets, especially in the oil and gas industry. There's lots of different applications that can be had with an Organic Rankine Cycle. We are basically hot water, so it's fuel-free, emission-free. We don't combust anything, and as long as the process that we are compared to like solar or wind, we are base load power if it's an operating 24/7, like the flare application that we're going to discuss today. Our primary market focus has been stationary engines. I'm going to talk a little bit about that at the end, the natural gas compression engine opportunities. We've started to do boilers and flares like the demonstration we have here today. We've also done biomass projects, process heat in an industry, and even geothermal, which could be related to co-produced fluids coming out of the ground in the oil and gas industry. Next slide, Rich. So a basic Organic Rankine Cycle, if you think of a steam cycle, which is the Rankine cycle, basically you take hot water, which is the working fluid, or the hot water, and you create steam. Steam creates pressure. Pressure is released across some expansion device, and you spin a generator through that pressure. The exact same physics occur in an Organic Rankine Cycle, except we don't use water as our working fluid. We use a refrigerant that basically wants to boil at 58 degrees Fahrenheit. So if something wants to boil at 58 degrees Fahrenheit, if you put something at 200 or 220 or 230 F, like we are at the site in the Bakken, you basically get the exact same physics. We spin a screw expander, and out come the kilowatts. So by taking the working fluid down to something that wants to boil at 58 degrees F, now you can have much lower input temperatures to drive the exact same physics and get beneficial use of waste heat. The example I have at the bottom is just if you think of an engine, a reciprocating engine, larger than the one in your car, but same basic concept. Jacket water and exhaust, you may take 1 unit of fuel in, and about 35% of that unit of fuel efficiency gets used. 65% typically goes to waste heat. It's a great opportunity to capture that waste heat and add more power to a site. Next slide, Rich. So if you look at our fleet, we have a fleet of 52 units installed across the globe. I'll show you where in an upcoming slide. We have 12, and actually we have 13 in process. We got a PO from Hungary this week. Basically, a lot of our focus has been engine gensets. So the waste heat, jacket water, and exhaust from an engine genset is a perfect application for an Organic Rankine Cycle. You can see that we have a lot of biomass activity that's mainly from Europe. We've done district heating systems in Europe. That's a large Rolls-Royce turbine, basically the condensate off the steam turbine used for district heating. We take it and make more additional power. We've done geothermal sites. We have a site going into Japan. Loy has done a co-produced fluid demonstration in Mississippi that I'll talk a little bit about. We've done concentrated solar, industrial process heat, and now the flare. And basically what this says is there's lots of opportunities across many applications. The oil and gas industry is a great opportunity for us. Next slide, please. So to give you a feel for where we are across the globe, and this speaks to the robustness of the machines. I mean, we're a small company based in Reno, Nevada, but we do have a global reach. We've placed 52 machines across these countries, and like I said, we have Hungary to add to this list. We're happy about that. But one thing that speaks to the robustness, most of our clients, their second or third language is English. We literally have a site in Italy where if there's any operational concerns or issues, we text or email instructions to investigate the machine, and the gentleman Google translates our English translation of how to service the machine into Italian and works on the machine. So, and we've heard this from the HES crew at the site. You know, our target for this site was flare reduction, number one, but do it simply and do it robustly. And I think we've proven that over the last 3 months, and we're successful and happy about the fact that we have a simple and robust piece of equipment that's commercially available. Next slide, please. A little bit further on that, here shows the fleet growth. We went commercial in the end of 2011 for our commercial product launch. The company's been around for a decade, but really didn't get serious about commercial production until the end of 2011. And you can see, of all the machines, the vast majority of our machines are internet connected or wireless, and we can monitor the operation of the sites from Reno. We can start and stop the machine. We can trend data. We can have alerts and alarms be sent to iPhones, et cetera. So it's a very robust, mature system. And you can see along the road there's some lessons learned in there where we dipped and skinned our knees. That's part of putting real hardware into real environments. And you know, Loy will get into the operation of our unit. We had one sensor fail on our piece of equipment on the Power Plus generator in the 1,500-hour trial, and it was replaced by an electrician who never worked on a Power Plus in his life, and basically was up and running back in an hour when we knew that this sensor had gone bad, and we had a spare part in the machine, and it was off and running again. So we are very proud of the 97% uptime. Next slide, please. So I'll talk a little about the economics of a Power Plus. And you can see various modes of technology here, from diesel to biomass to geothermal, et cetera. These are DOE numbers. And this is basically, if you think about this, is a 20-year capital. Our piece of equipment is a 20-year design life. And then fuel component, which our fuel is zero, and then operating expenses for maintaining the unit over the 20-year lifespan. So if you know, diesels, and I said reciprocating engine is a major focus for us, and we do have diesel sites in Alaska, and now we have one in Cuba. We're actually commissioning one today down in Guantanamo Bay on the Navy base. And the focus there is savings from making power off the waste heat. And you can see if you give me enough waste heat, the green bar, to make 35 kilowatts, we're at about 7-cent power. If you give me enough waste heat to make 65 kilowatts, and I'm at 5-cent power. And you can see the economies of scale here as you go up larger, up to 110 kilowatts, our largest machine for now, and that's about 4-cent power. At this trial for HES, the goal was flare reduction and, you know, the economic benefits of displacing the retail cost of power. But the major goal is flare reduction. On some of our sites, it's very economically driven. On some of our sites, it may be a cooling opportunity. We are a cooling machine. But on this site, it was basically displace the retail cost of power. You don't have to get a purchase power agreement with the utility. We're behind the fence. We don't export. We're small enough capacity, output capacity. And then hopefully we have beneficial use of the flare, which we've proven. So this is one way to look at the economics of a Power Plus system. The other one is everybody's going to ask, you know, what's the capital cost of the equipment? So for our standpoint, every installation is different. You're going to find this in the oil fields too. It depends on which Power Plus, which size of machine you choose, what type of cooling you need provided, Do you want an integrated package, which I'll touch on in the upcoming slide, or do you want a standalone system, et cetera? But the bottom line is we've done installations somewhere ranging in the $250,000 completely turnkey installed to the $500,000 completely turnkey installed type of numbers. And it all depends on what part of the world you're in, what labor costs are, and how much engineering and installation content the customer might want to take on. So on this particular site, we actually had our equipment integrated, fully integrated. I'll show you a picture of it coming up. And then we rented a low NOx boiler for the demonstration. So those two pieces of equipment would have to go together. Next slide. So here you can see the three product lines. We'll start at the bottom. We have a 35 kilowatt system, middle 65 kilowatt system, and then the 110 kilowatt system. And as the little box there says, the three output levels, but they can be packaged with a cooling circuit or standalone. So an organic Rankine cycle needs cooling. So that's the radiators associated with the top and the bottom picture. And we can fully integrate that for you at ElectraTherm. So everything's plumbed. You have a pump, you have an expansion tank, you have all the controls, talking to the radiator, et cetera. So it's a fully integrated package. That's what we deployed in the Bakken at Hess. And although we do have some distributors and customers that want to do that work themselves, so we also sell the standalone equipment. But most of our proposals these days are going with the fully integrated systems where all the work is done here. And literally, we'll go to the next slide, please, Rich. So literally here on the fully integrated system, and this is the type of construction that we did at the Hess oil site, is the integrated cooling circuit is supplied. Number two, there's a hot water in and hot water in and hot water out is the only mechanical connection. So the boiler feed and then boiler return, and then an electrical interconnect. And Loy will get into it. I mean, we literally had 2 shipping containers set up in about 2 days, and he'll go into the specific commissioning. So it's a pretty flexible system, and it's easy 1 to 2 day commissioning. Next slide, Rich. And then finally, at the same time that HARC was interested in working with Gulf Coast Green Energy and trying to find an opportunity on a site with an appropriate flare, and thankfully Hess came about and offered that site. So we appreciate all of the work that HARC has done, the work that EFD has supported, and Hess allowing us to be on their site. At the same time we were learning about the Hess opportunity or the flaring opportunity, we were learning about wastewater treatment plants and methane abatement. And what we're learning about wastewater treatment plants, it very much relates to the oil and gas field, that methane is a waste problem unless you can capture it and put it into a large reciprocating engine, a gas turbine, or something like that. But if you go to areas that are remote or small or don't need the power, the problem becomes you've got all this excess methane, like the 3,000 wastewater treatment plants there are in the United States that produce methane, and their only opportunity is to flare. Because the capital intensiveness and maintenance intensiveness of putting large power plants in, it gets very expensive and very capital intensive and maintenance intensive. So we learned that at wastewater treatment plants that already have boilers because they have to heat the anaerobic digester. So if you look at a wastewater treatment plant, they have waste methane, they have boilers because they heat the digester, they create hot water. The only thing they really need is a power plus to create some on-site electricity, reduce their flaring, the exact same problem that's going on in the Bakken, reduce the flaring, put the flare to beneficial use, and then there's also an opportunity to take the condensing side off of us and use the extra heat. So we could actually heat some processes on the oil and gas field site, or we could actually heat the anaerobic digester with our condensing side. So methane is becoming more and more of an issue, whether it be a landfill, a wastewater treatment plant, an industrial wastewater treatment plant, or the oil and gas fields. And with that, we've put our first demonstration in reality, set it up into North Dakota, and Loy's going to talk about the specifics of the sites and the project.
So over to Loy.
Loy's on the...
Loy?
Rich, I apologize. I followed your instructions, and I was on mute. So, but thank you, Rich. And I just want to thank you, Rich, and EFD for giving us the opportunity to do this demonstration. Before I get started and tell who we are and about the project, I want to thank John and his engineering team for working with us for over a year and a half to get the details and engineer this solution. And then most importantly, I want to thank the folks from HES who are on this call and those who couldn't be for giving us the opportunity to be on their site and demonstrate this solution, because we think it's a great opportunity to put flare gas to a beneficial use, not only in the Bakken but in other places that are flaring. But our company is Gulf Coast Green Energy. We're based just outside of Houston, Texas. We've been in business about 8 years. We represent ElectraTherm, and in fact, we were the first representative for ElectraTherm 8 years ago, and put the first Organic Rankine Cycle in a commercial application, and that was on the campus of Southern Methodist University in Dallas. So we've been growing right along with ElectraTherm, and we've got a really good team, and we've been enjoying working with HES and the folks at ElectraTherm on this project. So, Rich, I'm going to scroll through these pretty quickly, and I know you mentioned it early, but there may be some who have joined us since we got on. John and I have kind of practiced this along with Rich at this presentation, and we'll have time at the end of our presentation for question and answers. And again, if you joined us late, there'll be a little chat box down at the bottom, and you can type those in, and we'll be glad to answer them at the end of the presentation. So let's go right on into the first slide, Rich. So John talked about some of the heat sources. He described what our Organic Rankine Cycle does and some of the opportunities that we have found. These are opportunities that we've done and we found as Gulf Coast Green Energy. One of the things we like to say about our ORC, the Power Plus generator, is that it's really heat source agnostic. We're here on a flare project, and we can use just about any heat source as long as there's enough BTUs in the heat. And so some of these examples are solar thermal that we've done 3 of. The furthest one is on the island of Cyprus that our company did. The next one that you see at the top of that slide, as John pointed out, that's really our sweet spot for the technology, is on reciprocating engines. That's at a gas compressor site in South Texas. So is the one over to the right that you'll see there. That's our first gas compressor site that we actually installed and commissioned a unit. Gas compression, compressed gas needs to be cooled. We can take about 50% of that cooling load off of a gas compression site or a gas processing site. Rich mentioned the co-produced water, and I'm going to pause there just a moment. The middle picture in the bottom of your screen is a project that we did that actually led us to this project. We did a project that was funded by REPSI, and that was to make power from produced water. We did that successfully in Mississippi on an oil well, and we used the hot produced water to generate power there on a Denbury resource as well. Rich came to us about a year and a half ago and knew that we had done that site and it had been successful, and it was asking questions about, what other kinds of waste heat might we be able to utilize this technology. And then we all discussed that the flaring is a real issue, not only here in North Dakota. I'm in North Dakota right now, but in Texas and other states as well. We got together and our engineering team huddled with Rich and his team, and we decided that this would be a good application. And so that's really how we got started. And again, we appreciate EFD for their support in funding this project along with HARC, and again for HES allowing us to be on their site. And so then that leads us to the flare gas to power solution. And Rich, let's go to the next slide. I'm going to talk a little bit about the installation. John mentioned about how easy it is. This was the installation we did on produced water. And folks, you can see there that we got to the site at about 7 o'clock in the morning, dollied down our equipment. We hooked the picture to the right is where we hooked up the hot water source and the return to our ORC. And then down at the bottom, not all those folks, it only took 2 of us to commission that, but we had some folks that came in from the oil company from Dallas and wanted to see it. So by 3 o'clock in the afternoon, we were making power. So the equipment is very transportable, it's mobile, and it's easy to install. So next slide, Rich. So when we were talking to Rich and the folks at EFD and HARC, we realized that and we learned this from those folks and from the folks at Hess who we were working with early on there in Houston, that flared gas is a real issue for oil and gas companies. They don't like it. The infrastructure just does not allow them to be able to do anything different with it until that infrastructure catches up. So this was the challenge that we saw, and so our challenge is to try to reduce that flaring and put that flared gas to a beneficial use. And so I'll pause there just a moment because I'm sure there are some that are on this call that are not in the oil and gas industry. Those that are in it already know about it, but I'll pause there just a minute and let you take a look at that, and that was from the Wall Street Journal. Okay, Rich. So our solution that we developed, you can see up on the top left, that's a picture of the flares where this unit is here in North Dakota in the Bakken. And so our solution was to, as we discussed before, fuel the boiler that you see up at the top. It's a 150 horsepower Cleaver Brooks low NOx boiler. We designed the burner for 30 parts per million NOx for this. It can go down to as low as 9 parts per million. But we've brought a 30 part per million NOx boiler to the site for this demonstration. And so that's what heats the water. John's described how the ORC works. The hot water is delivered to the Power Plus. In this case, the site is using all the power that we use, and some of it is actually going back to the grid, or at least it was when we first commissioned the units. And of course, our goal over there is to extinguish those flames and take that gas and put it to a beneficial use. In this case, power that can be used on site or that could be used at other sites by the company.
Hey, Loy, let me just add something here too. And as people know, they might be familiar with the flaring issue. The reason those flares are variable, and they vary with time. They vary liquid content, they vary BTU content, they vary with H2S content, etc. And the boiler is a very robust design boiler, and it can take the raw gas or treated gas into the boiler with the same burner. And as we described, Loy described, we picked a 30 ppm NOx burner. And so all the challenges that the flare gas presents, just like at a wastewater treatment plant with siloxanes and everything else that goes into this, the industrial boiler takes on the hard work for the site and dealing with that flare gas. And then the Power Plus basically has a hot water loop running through it. So all the work is done by that 100-year-old technology there, which is great.
Yeah, good point, John. Thank you. Okay, Rich, let's see the next one. We'll start talking about the installation and the ease of the installation. Oops, I'm sorry. This is the one line that gets you there. So you can see where the well and then as John said, we designed this boiler to be able to use raw gas. Where we've got treated gas that is being used right now for this project, but this boiler is designed to use either one. Of course, it goes through a gas regulator. We're using the 30 part per million NOx burner, and you can just walk down through the rest of that one line. Again, we're using a 150 horsepower hot water boiler. That boiler, incidentally, is capable of generating twice the power that we're generating and consuming twice the gas that we're using there. We brought the mid-size Power Plus generator to this because it was a demonstration. But at this site, this same boiler could support 2 of those. of the units that we brought. So we could make double the power and utilize twice the gas that we're using for beneficial use. Okay,
and
Rich.
Lloyd, Lloyd, before
yes.
we go on to the next slide, we do have one question that's come in here.
Okay.
You say you could put the electricity on a grid and transfer it to other sites. Does North Dakota allow you to run your own electric lines, or are you required to utilize existing electrical power for a distribution and or transmission?
Yes. Rich, thank you, and I appreciate the person who asked that question. And in fact, I'll pause there just a minute, because that's one of the really neat things about this technology is that Delta Contractors here in North Dakota did the electrical work for us. And basically what they did was put in another breaker there on site at the site. And it takes 3 wires in the ground, and within 30 minutes the connection was made. And so we're actually hooked up to the grid. Some of the good things about the Power Plus generator is that it has an induction generator in it, so we cannot backfeed the grid. So if the grid goes down and our generator goes down at the same time. Power companies like that. We're working with McKinsey Electric Co-op here, and when they understood that this was that kind of a generator, an induction generator and not a synchronous generator, that took a lot of their concern away. Additionally, because we're hooked up to the grid, the power actually just goes into the grid. At this site, what they're doing is that they're paying the amount of gas or electricity that we're making is offsetting the electricity that the site would be purchasing from the power company. When I said that it could be used at other sites, in many states, I know it is in Texas, and I think that it is in North Dakota, is that if there is another unit somewhere, so say we're making a surplus of power on a site, if there is another power use on that company's grid, on the power company's grid at another location, that power can be utilized to offset the power at that site as well. So that was maybe a little more detail, and hopefully that answers that question. Okay, Rich. So this is how we got started. This is at the factory, at the ElectraTherm factory there in Reno. The left picture over there was a Power Plus generator on the test cell, and then it got moved over to the frame that you see there to the right. And I'm going to scroll through these almost kind of like a video. So Rich, we'll go to the next one. Again, these were the flares when we arrived at the site. These were the flares that were burning. Next slide, please. And then this is when we landed the equipment. So one thing I'd like for everybody to kind of take a look at is the length of time that it took us to do this. So we landed the equipment. The picture on the left is the Power Plus generator being unloaded and set in place. The picture on the right is the boiler, and all of its associated equipment is in that container, and it was set up right next to the Power Plus generator. I might mention that's a 100,000-ton crane, which we didn't need that kind of capacity, but that's what Roscoe had available. Roscoe Crane out of Minot had available for us. We can actually unload this equipment with a large forklift. So that was day one. Next slide. We finished out day one, and also on day two, you can see that there were connections being made up on the top left. That's actually Chris that works with Rich. He's one of the engineers at HARC. He and Satish came along for this installation, and we put them to work. So that's Chris over there making sure that all the connections are good and tight after the trip up to North Dakota. And then our guys are down there at the bottom and flanging up some of the fittings, and then over to the right is one of our guys, and then the ElectraTherm chief engineer or engineering manager at ElectraTherm, Tom Brokaw. So that was end of day one and beginning of day two. Okay, Rich. This is a view of the boiler for those of you who are interested in that. It's fairly simple technology. As John said, it's 100-year technology. It's proven. The real the real critical part of that boiler is the burner, and I'll go back and kind of reiterate what we talked about. So the burner was designed to be able to burn raw gas or fuel gas. We had the gas analysis that Hess provided to us for both fuel sources, and so that boiler will operate where there's treated gas as it is now, or it'll operate also on raw gas. So you can see the left side of the container. Of course, that's the boiler. Over to the right picture is the water treating equipment. There's a little small water makeup tank there. I want to pause here and also say that the boiler is in a closed loop. It's a hot water boiler, so it's not a steam boiler. So we don't have to have on-site trained personnel and permits and all that. It's just basically like the hot water heater in your house. And so there's really no reason or need to have makeup water. We've got that there in case of an emergency that we need to add water to the boiler. So it's in a closed loop, and as John said, the ORC is in a closed loop as well.
And Lloyd, before we go on to the next slide, we do have another question that's come in. And
yes, sir.
The question is, what advantages does this system have over a microturbine that could theoretically convert flare gas to power in a single step?
Yeah, and that's a good question. And, you know, one of the things that, and I was asked that question here in North Dakota today when I was visiting with the Industrial Commission. And, you know, our equipment uses waste heat to generate electricity. So if there's waste heat on a site, if it's a reciprocating engine, if it's a turbine, if it's a microturbine, we can use the exhaust from that to generate additional electricity. So our equipment really works in any application. The difference in ours for a flare operation and other heat sources as well is that boiler will burn raw gas. So we don't have to treat the gas. The gas can be burned in that boiler directly, and so there's no need for gas treating equipment, or then as far as the environmental concerns are, the emissions out of the boiler are much less than there would be out of other power generators, if that's a reciprocating engine or a turbine. But again, we can complement those kinds of units, or we can be a standalone in place of. The point of it all is there is so much flared gas, not only here in the Bakken, but in other states as well. You know, all technologies we think need to be looked at and deployed. And we know that the company that we're doing this project on their well site, they're looking at all sources and technologies to try to reduce flaring. But the advantage, again, that we think that we have is that there's no gas treating equipment. Our emissions are much lower than from a reciprocating engine or a turbine. So I hope that answered that question, Rich. Okay, next slide. And so again, this is day 2. You can see John was talking about the refrigerant. Those are refrigerant bottles that one of the guys, I think actually that's the ElectraTherm guy toting that bottle there. And so we were charging the system up. The picture on the lower left was when we were pulling the cable, the power cable. Delta Contractors, the guy in the blue hat's right behind me. And it was a big tug of war. That was an all hands on deck for pull that cable. So we got the cable down to the Power Plus, and then Troy with Delta Contractors is there on the far right. He closed the breaker, and we were ready to make power. So that was at the end of day 2. And then the next slide. Yep.
Okay,
go ahead,
Lloyd,
Rich.
First though, Lloyd, we got another question that's come in, and this person is concerned about the low ambient temperatures. So with low ambient temperatures, could you use a glycol or oil instead of water through the boiler for the heat transfer?
You know, we've talked with the boiler manufacturers, Rich, and for the person who asked that question and others who may be wondering, and we've worked with a couple of boiler manufacturers to design this system. We knew that this was going to be a 90-day trial and that we would be out of North Dakota before they get really cold here. And so as far as the boiler is concerned, it's ready to be winterized, and then yes. So the question was, would we use glycol? And so in the boiler, yes, if this unit stays here, you know, we'll put 50% glycol in it. Talking with the boiler company out of Fargo, North Dakota, who's been servicing this boiler for us, that along with a heater that runs off of gas with a thermostat, when it gets down to 20 and 30 below, that heater comes on to preheat the air that is used by the boiler. It can be winterized, and there's boilers all over North Dakota that operate 12 months out of the year. As far as the Power Plus is concerned, like John said, I mean, we've got units running up in Alaska, units that have been installed in Alberta, Canada, and so the radiator there, we put about 50% glycol in that radiator as well, and so that system is already designed for cold weather. So I hope that answered that question. So then that brought us to our day 3, and the system was successfully commissioned and was generating power, and has been generating power now for the last 90 days. You can see that's the top picture is kind of a panoramic view of the site. It's a beautiful site that Hess has there, by the way, and I want to pause there just a moment and say that the folks at the asset, the operations guys there out of the Keene office have been just great to work with. Thankfully, we've not asked them to help us out very often, but when we have, they've been Johnny on the spot. And I was at the Keene office yesterday and visiting with some of them, and they're just a great group of guys, and they've just kind of got that can-do. There's nothing I don't think those guys can't do. So we appreciate their assistance on this. Down there at the bottom is our team. Again, it only took 2 people to do this, but we brought the whole crew with us, along with the HARC engineers, and then Tom Brokaw is the engineering manager for ElectraTherm. So that rounds out the commissioning, and I think there's, Rich, if you'll go to the next slide. I know that John is going to follow this up before we take more question and answers, but let's see what this next slide is.
All right.
Yeah, this gives you an idea of since we've been here, our total run time is 1,535 hours. We've not been down for long, and we've not been down many times. And so the total kilowatts produced is almost 81,000, and that was, I took those readings this morning at about 5 o'clock. Incidentally, I can read all of that information from my phone or from my computer, and so ElectraTherm has got some great controls, and they got some great remote monitoring. We can operate that equipment. Obviously, any adjustments have been made out of Reno or our team, and we're thousands of miles away. So it's a great system, and we consider this has been a really good demonstration and a successful demonstration.
And Lloyd, before we turn it back over to John, there are a couple more questions that have come in. First of all, is there any economic advantage to using a microturbine on the front end with this in addition?
You know, I'm going to ask John if he's studied any of those kinds of applications, or if his engineering team has. We have not studied an application like that on a flare gas. I can tell you, you know, and we're not experts in microturbines. I mean, obviously we know about the technology, but we kind of tend to our own business with our ORC. What I can tell you, though, is that if there is a microturbine, or if there were a microturbine or a reciprocating engine that's using flared gas to make power, we can complement that unit, and we would like to take a look at those units with anyone who owns it. John, do you know of any projects like that?
Yeah, well, and this is John Fox talking, and I'm familiar with the microturbines, and we've looked at the waste heat provided from like 65 kilowatt microturbines, and then the 200 kilowatt microturbines that we're familiar with. It takes about 3 65 kilowatts, maybe 4 65 kilowatts to produce enough hot water to run an organic Rankine cycle, so you can definitely capture the waste heat. And Capstone, a familiar provider to those, has a top hat, they call it, that actually turns the exhaust into hot water. So there are designs for microturbines already that convert the exhaust into useful heat, and we could be an add-on for that type of scenario. So that's we would be interested in discussing that further. The challenge that I've understood from a microtubin standpoint or any prime power standpoint that we've been talking to customers that own different types of prime movers, including fuel cells and engines, is that it's the gas treatment that's the tough part. When the BTU content is varying all over the place and the liquid content is varying all over the place, and that becomes an issue for something that wants to basically maintain constant speed. So with the boiler, like I said, the boiler just sits there, and we don't care if the boiler gives us a little less hot water or a little more hot water from a flow standpoint. Our set point on the boiler for this was about 232 degrees, and as the flare does its thing, the boiler takes care of that. So we kind of have a buffer in between us and the flare gas. So there's, like we talked about earlier, there's opportunity. Waste heat's everywhere, and if there are systems that are going in, and even for this site, I mean, those are massive flares. If somebody wanted to put down, 1 megawatt reciprocating engines, was going to be my next slide, we would love to be the radiator on that 1 megawatt engine. Engines are a great source of waste heat, and so are microturbines.
And John and Loy, we got another couple of questions here. First of all, about the refrigerants used. Is the refrigerant you use environmentally correct? Are you using pentothal to reject the heat of condensing? What is the maximum temperature at which the process would become inefficient?
Yeah, the refrigerant is R245FA, and it's manufactured by Honeywell, and it's Kyoto approved. It's non-corrosive, non-flammable, non-explosive. John, I'll let you answer the question about the upper limits, and we'll share this question.
Yeah, so Loy's been watching the temperature in North Dakota. It's going to get into the 20s next week, the Fahrenheit. The Power Plus will make more power as it gets colder out. You're a heat engine, so the delta T, the delta between the hot input and the cold side, drives the efficiency. We've looked at sites, especially in the wastewater treatment world, where the anaerobic digester wants about 100 degrees F, and we can actually use the condensing side of us to heat the anaerobic digester. We've looked at installations where you could do radiant space heating for floors, heat swimming pools, etc. So the efficiency does drop off as we go higher, but if you have enough delta T, about 80 to 100 degrees F, the efficiency will stay constant until we clip on the high side of our high temperature. So we have run our test cell as high as at least 120, maybe 130 F. Ambient. We've run in the parking lot. I'll describe an engine test that we did for the Department of Navy. It was about 100 degrees, 105 degrees in our parking lot running our system, and the efficiency was good because we were driving the system hotter also. So we raised the high side temperature to compensate for the high ambient. But you will get varied output. During the day the output may go down a little bit. During the summer the output will go down about a little bit. During the night time you'll have more, and during the winter you'll have more.
And our next question here is, what was the target temperature for the heated water? The ultimate for us is between 240 and 250 degrees F, and this boiler was set to about 232 degrees F. So we would like it a little hotter. Our major goal for this demonstration was to show the potential. Like we said, we have a larger piece of equipment that would have taken more flare gas. We could have rented a larger boiler, et cetera, but we wanted to prove that we could put this equipment in a very remote area without a support staff. None of our people have traveled to North Dakota besides for the commissioning. So our goal here was to demonstrate the technology on a remote site with limited input to having the operation and maintenance of the site, and so that's kind of what it wasn't all about kilowatts at this site. It was more about reducing the flare and improving the technology.
John, I might add to that. Just a moment, Rich, and I might add to what John was saying, Rich, is that because I've been asked this question, I don't think we mentioned it. Now, the oil and gas folks who are on this call probably already know the answer or suspect the answer, but if you're not oil and gas, you may have the question, what kind of personnel are on this? This is an unmanned site. And so, I mean, obviously, the company has company men that check on this site continually, but it's basically an unmanned operation. There's people that come and go. but there's no maintenance crew that's on the site that's checking on our equipment. And again, the guys out of Keene have come out when we asked them to, and have done a great job of. Usually it's just turning a switch on. So they've helped us out on a couple of other occasions, and but it is an unmanned site. I'm sorry, Rich, go ahead with the other question.
All right, I've got one more question before we move on, and that's what's the startup time for these units? Could it be used as a backup power source if hot water was immediately available?
Yeah,
once we get the equipment there, it's just a matter of flanging up the heat source. I mean, if there's already hot water and it meets the requirements for our equipment, it's a matter of basically, if the company brings us the heat source in flanges that we send all that information to the company. We could, feasibly, if the equipment were delivered first thing in the morning, we could be generating power before the end of the day.
Yeah, and the startup time for the machine's about 30 seconds for it to start up. For it to literally do its start routine. It's not going to be a diesel engine that can ramp up in 5 seconds or something like that. It does take a little bit of time. It's got some momentum for the heat to get balanced in equilibrium in it, but it's about a 30-second startup, if that's more the question.
And then, John, I'll hand this one back off to you and let you discuss a little bit more about the stationary engines and our radiator replacement solution.
Yeah, thanks, Loy. So to wrap up here, I just want to, because we have so many oil and gas folks and others, like I said, reciprocating engines are a great source of waste heat. Typically, they're in the 30 to 40% range in efficiency, and so that means that the vast majority of the waste heat is generated in the jacket water and the exhaust. We've done, I think it's 37 installations, I think it was from the chart before, on engines. We've done single engines, multiple engines, jacket water only, boosted jacket water through the exhaust, et cetera. So we really have some expertise in how to capture the waste heat from an engine. Typical engine sizes that match up nicely to our equipment is a 500 kilowatt engine matches nicely with a 35 kilowatt unit. A 800 engine matches nicely with a 65 kilowatt unit, and the 1 to 2 megawatt engine matches with the 110 kilowatt unit. So engines, and the opportunity in the oil and gas field, as everyone knows, there's thousands of reciprocating engines that usually have no use for the waste heat on a natural gas compression site. So if you go to the next slide, Rich, we partnered with the Department of Defense and contracted with the Navy. This system here is a 2 40-foot containers, just like the two 40-foot containers you have in North Dakota. But we contracted with Cummins. The Navy gave us a 1.1 megawatt Cummins engine, and they packaged the system for us in a CHP, combined heat and power configuration, where we actually took the jacket water and the exhaust from the engine, captured all the waste heat that we possibly could. We literally threw out the PTO shaft-driven radiator. It's actually sitting in our shop. And we took that load off the engine. So the important thing for the gas compression people out there is that when you have a shaft-driven radiator, you're taking about 5% to maybe even 7% of the engine's work, available work, to cool the engine, which means you're not compressing gas, which means you're not increasing your revenue. So when we did that, between the output of the ORC and the reduction in cooling load, because we took the horsepower requirement, it's about 75 horsepower fan sitting on front of this engine. We took that load off the engine, added electricity, and for this combination here, it's about a 10 to 11% improvement in fuel consumption. So we had a third party called Southern Research. They did the baseline with the engine as it was initially configured, and then they've done it again at Port Hueneme in California. And the units, the CAD drawing units that you're looking at right there, are actually in Guantanamo Bay right now, and they're going to become part of about a 12 megawatt base load power plant that the Guantanamo Bay Navy base runs on. And we have a 2,000-hour demonstration coming up with the Navy, and it's just about to be commissioned. So in the gas compression world, the mentality of doing shaft-driven gas compression, this could be a paradigm shift where we call it the radiator with a payback. And what we mean by that is we become the cooling device, and we're 100% redundant. even if the ORC is down, it doesn't matter. That radiator there is the radiator for the entire system, for the ORC and the engine, and we're fully redundant, so even if we have a maintenance issue or for some reason the ORC is down, there's no issue with the combined cycle. So we'd love to, and Rich has even offered to learn more about this and potentially contact HARC. He would be interested in talking about a potential project for doing a natural gas compression, high efficiency natural gas compression engines. So with that, I'll turn it over to Rich and he can close out the meeting.
All right, very good. Like we said at the beginning of the webinar, we expected this to last an hour, and we'd like to be respectful of people's time. We do list all our contact information here. If you would like to get in touch with any of us, you want to talk about different field trials that you would like to have on the equipment, we'd be happy to accommodate that, so please contact me. If you want to know more about ElectraTherm or Gulf Coast Green Energy, we got Loy's number and John's number up there. This webinar has been recorded. I know we have some EFD sponsors online. If you would like your own private discussion with any of the team members, well, that's part of being an EFD sponsor. You get that benefit. So just give me a call, and we would be happy to arrange that. We apologize to any of those that co-workers were not able to get online and see the webinar. We will discuss whether or not to offer this again, and we will also, as I said, it has been recorded, and we will be having this up on our website with a link. So here's our contact information for myself, for Loy, and for John. Either jot down those numbers or visit some of our EFD websites, in particular the EFDsystems.org, and check us all out on all the other projects that we have going on. So if there's, I see there's no further questions, so we thank you for your time. It has been an hour, so thank you. We wish you a good evening, and have a nice, safe drive home from work or wherever you're headed to. So thank you very much, people.
Thank you all very much. Yep. Thank you, Rich. Thank you, John.